Okay, so welcome to seminar number 12. And today we're going to talk about the NASA JPL mission to Mars, which is going to land in 2 days. So the name of this mission is Mars 2020, the year in which the mission was launched from Earth. And the reason why there's so much interest in going to Mars is that it's one of the nearest places in the cosmos to Earth. And indeed, we can get there even with conventional rocket technology. We don't have to develop any dramatic new propulsion systems as we would to get outside of our solar system. And Mars has the most potentially viable habitat other than Earth that we are currently familiar with. There may be exoplanets around other stars that have better habitats than Mars, but we certainly don't know about those yet, and it will be a long time before we can be as certain of their habitats as we are of Mars. And indeed, the habitat of Mars may have once in the past supported life. And it may have had oceans on its surface and life in those oceans. And indeed, there are people who believe that life did exist on Mars and that we, in fact, may be the descendants of that life. So NASA commissioned a study by this gentleman from Georgia Tech. I don't know that NASA endorsed the results, but they funded the research. This is the reference code if you want to look it up on the internet. Archive ARXIV is the science publication website that's been established by Cornell University, and scientists in all sorts of different subjects of study can publish their works immediately on that website. So all the good stuff comes out on ArchiveX. Now, what Mr. Carr proposed in this paper was that life did begin on Mars and was subsequently transferred to Earth by meteors. So when giant objects impacted the surface of Mars, they knocked a bunch of Martian soil and oceans up into the heavens. And some of those objects fell back into the inner solar system and hit the Earth, and thereby carried that life that originated on Mars to Earth. And if that is indeed true, then we are really Martians. He makes the claim that all of the primary biochemical ingredients that are essential to life, the amino acids, the nucleic acids, and the lipids, which in that sequence support the metabolism, the genetic code storage, and the chemical isolation of all the life we know, that all of this life naturally could form via certain chemistries and under exposure to ultraviolet light on a dry piece of land. And that this is more likely to have occurred on early Mars than on early Earth. Now, he makes the following claims: that the early Earth, in the very beginning, the surface of the Earth was covered with molten rock, with magma. And once that magma cooled, the surface of the Earth became covered with water. The entire surface would be covered with water, he imagines, in the beginning. And that it took several billion years before there was a substantial amount of land area on Earth where this chemistry of water interacting with the rock and the land could produce the molecules of life. He also makes the claim that was, which I think is well agreed to by other scientists, that oxygen first appeared in Earth's atmosphere only about 2.5 billion years ago, after plant life started generating oxygen as a byproduct of its metabolism. And yet he says that by genetic dating, scientists have been able to determine that all life on Earth seems to have come from a common ancestor. And that common ancestor, called the last universal common ancestor, or LUCA, if you project the mutation rates backwards in time, you find that LUCA may have arisen 4 billion years ago. And 4 billion years ago, he said, life, the Earth was not hospitable to life, but Mars was. So he has all of these, interesting points to make. None of them is completely definitive, but it's an interesting conversation. He says that by comparison to the early Earth, Mars always had a substantial amount of land and in the land area, and in the beginning it had also oceans of water and lots of water in certain parts of the surface. It had all of the key chemical elements that life requires: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And our Curiosity rover that has been on Mars for a couple of years now has found evidence of this water rock chemistry that could potentially generate these biochemical molecules. And that evidence dates back as far as 3.7 billion years ago in the Gale crater that Curiosity rover has been exploring. So the purpose of the next mission to Mars is to try to find evidence of that early life on the surface of Mars. This very busy chart comes from this paper by Carr from Georgia Tech. I'll try to show you the important parts. At the top is the graph of when land area became common on the surface of these two planets. And Earth was only within the last 3-ish billion years, but Mars always had at least half the surface covered by land. Mars had a magnetic field. It is claimed at various points in its early history. We know it doesn't have a strong magnetic field now. Whereas Earth's magnetic field, which is very strong now and protects our atmosphere, developed, they say, only about 3.5 billion years ago. He's talking here about the existence of subsurface water and then surface water, and the existence of the various chemical elements that are essential to life. And then finally at the bottom, this is LUCA, the original common ancestor of life purported. And he says that could have evolved on Mars even before 4 billion years ago and been transferred to Earth by meteors. The first fossil evidence of life, which I'll show you later, dates back over 3.5 billion years. And there seems to be isotopic chemical evidence of life, which is more questionable, that dates back perhaps another few 100,000 years. So this forms a lot of the motivation for NASA to send missions to Mars and try to understand whether life really did exist in early Mars. So the mission goals are this search for life, and in particular, the rover that's being delivered to the surface will be able to drill into the rock and the soil and extract samples of ancient materials, and those ancient materials will be analyzed on the surface of Mars by the rover and possibly returned in the future back to Earth so that we can analyze them more extensively in our own laboratories here, which are far more capable than anything that we can launch into space. Also, this mission will be testing some future technology that would be very important if we in the future send men to Mars, a manned mission. Okay, so some of the key points of this Mars mission is the mission was launched at the end of July in 2020 on an Atlas V rocket. It's landing in 2 days at about 12:30 p.m. on Pacific Standard Time. JPL operates on Pacific Standard Time. They want to have the Earth facing, Earth in the position to receive the signal when the thing lands. And the duration of this mission, the planned duration, is at least 1 Martian year, which is about 2 Earth years. Okay, so a bit more about Mars. It's the 4th planet from the sun, and it's 1.5 AU. AU is the astronomical unit, and it's defined as Earth's distance from the sun. So Mars is 150% of the distance of Earth from the sun. It has a annual orbit around the sun, which is approximately 2 Earth years, and it has a relatively high eccentricity, which means its orbit is not very circular, but actually somewhat oblate. It's almost 10% further from the sun during one of its seasons than it is on average, and 10% less than that in the opposite season. And that is the 2nd most eccentric orbit of any planet in the solar system. The most eccentric orbit is Mercury, which is far more eccentric than that. It has a rotation period, a day, if you will, which is comparable to Earth, just a bit longer. And its mass is about 9 times less than Earth. Its radius is approximately half the radius of Earth, and its surface gravity is about 1/3 of the surface gravity of our planet. In terms of temperature, the minimum temperature on Mars is minus 226 degrees Fahrenheit. That's the minimum recorded temperature. The average temperature is minus 82 degrees Fahrenheit, and the maximum temperature is 95 degrees Fahrenheit. And then corresponding numbers in centigrade are next to those. So there's a wide swing in the temperature of the planet day and night, and during the course of the year, and across the surface from the poles to the equator. This is not a place that humans can easily live without significant protection, but it is better than many other places in the cosmos. There is very little pressure of the Martian atmosphere, only 0.6% of the pressure on Earth. And the atmosphere on Mars is almost entirely carbon dioxide. 96% carbon dioxide, about 2% argon, 2% nitrogen, and just trace amounts of these other gases. About 1/6% of oxygen, about 1/50% of water vapor, and parts per billion of methane. Methane is something that astrobiologists are quite keen on, and some of them believe that methane is a sign of life. Others dispute that. This is evidence. This is a X-ray fluorescence image, and it shows the face of a cliff on Mars. This is the highland. This is the valley below. This is the face of the cliff, and the purple area that you see here is ice. So there is subsurface ice, probably in many places throughout Mars, indicative of the fact that there has been water in the past. Okay, now let's turn to one of the highlights of what's coming up on Thursday, and that is the landing. It's easy to take off. It's much more difficult to land. You have to come to 0 velocity at 0 altitude. So these are the major stages in the landing sequence. The craft that has taken the lander to Mars, the cruise vehicle, is going to be jettisoned as before the lander enters the atmosphere. Once the lander enters the atmosphere, it's going to slow down by use of its heat shield, as do the missions on Earth that re-enter the atmosphere. It will then deploy a parachute when the velocity becomes low enough, and the parachute will bring the velocity to a much more controllable low level. Then there will be a power descent, so retro rockets will fire to keep this so-called sky train moving slowly down to a proper altitude. And then the sky train will lower the rover down to the surface on cables. Once the rover hits the land, then the cables will be severed and the sky train will fly away and crash somewhere else. So this is a sequence which replicates the landing sequence of Curiosity. One of the features of the Mars 2020 mission is they tried to invent as little as possible and use the proven technology that they've developed on prior missions. So in a bit more detail, the cruise vessel that lifted Mars 2020 off the surface of the Earth and carried it to Mars is going to be jettisoned about 10 minutes before time E, which is the entry moment into the atmosphere. And from then on, the lander is going to be on its own. And this is a new feature. The lander will find its own landing site and control its own landing sequence. And this is important because it's very difficult to do that remotely, because it takes 11 minutes for a radio signal to go from Mars to Earth and 11 more minutes for a command to be sent back to the lander. So the landing sequence is only going to last 7 minutes. So it's really very beyond the pale for controllers on Earth to be effective in adjusting any landing trajectories. Previous missions have landed by dead reckoning, and that's fine if everything works perfectly, but it's better if the lander has the ability to modify the landing to pick a better site if it sees that the landing zone is too rocky and that sort of thing. So this lander has its own navigation system and its own sensors to detect the major properties of the surface below. When it enters the atmosphere at time E, it'll be going at 20,000 miles per hour, and that will begin what JPL calls the 7 minutes of terror, which is the 7 minutes it takes to get from the top of the atmosphere to the landing. It's terror for the controllers at JPL because they can't do anything to fix anything if anything goes wrong. And they just have to wait with bated breath for the signal from the lander that says it's successfully on the surface. Okay, the heat shield reaches a temperature of over 2,000 degrees Fahrenheit about 1 minute and 20 seconds after entry. And the heat shield is maintained for 3 more minutes and jettisoned at 4 minutes and 20 seconds after entry. The parachute is deployed at 4 minutes after entry when the heat shield has managed to reduce the velocity from 20,000 miles an hour to less than 1,000 miles per hour. And the parachute carries the lander down at ever decreasing speed and is eventually jettisoned when the approach velocity is 200 miles per hour, at which point the retro rockets fire. At 5 minutes and 50 seconds after entry, which is about 1 minute before touchdown, the lander makes the final choice as to what the site will be, and then it power descends down to a velocity of only 2.5 feet per second. This is about 75 centimeters per second. And it hovers at an altitude of 67 feet over the surface. And the SkyTrain then lowers the lander down to the surface on cables. And touchdown of the lander will be 6 minutes and 50 seconds after entry into the Martian atmosphere. This is a artist's conception of what a successful landing will look like. Okay, and this is where we're going. So this is a topographic map of Mars. It doesn't include the north and south poles. This goes from plus 75 degrees latitude to minus 75 degrees latitude. And it includes all of the longitudes. Okay, and what we're going is right here to a place named Jezero Crater. And this is what it looks like on the travel brochure, Lake Jezero. And it once the rivers flowed in from the highlands over here on the upper left and created this beautiful lake. And the outflow of the lake was down here toward the lowlands. And if we had arrived about 3 billion years ago, then this is what we might actually have seen. So this is a blow up of the topological map topographic map we saw before. The water flow entry into the lake is this one. You see these alluvian flows that are typical of the major river flowing into the ocean. And the drainage of the lake is out here toward the lowlands. So the landing will be in this area. The rover will explore all of these alluvian formations and then collect samples and store them somewhere in here, possibly for later retrieval. We'll talk more about that. This is the NASA brochure advertisement of the rover. It's got a extendable arm with a drill mechanism and sample capture and storage head over here. It has 6 main wheels, 2 bumper wheels in the front, and that is not a steering wheel. Although it looks like a steering wheel, there's no astronaut on board. And then all the rest of this is the rest of the gear that we'll talk about, including a bunch of cameras and detectors. The whole object weighs about 1 ton, 2,000 pounds, 1,000 kilos. Okay, so the plan for gathering the samples is that with the various detectors that the rover has, it's going to go around and look for samples of rock and soil that show hints of being having interacted with water to form the chemicals that might eventually develop into life. It's going to drill down 2 inches below the surface to get an unadulterated sample of the old rock and soil. And it will do a preliminary analysis of those samples with its onboard instruments that we'll describe later, and place 15 grams worth of that material in a hermetically sealed tube. And that will be 1 sample. It will collect up to 30 samples and store them in a cache. And that cache will be left on the surface in a convenient location. And if the samples are intriguing enough and Congress is generous enough, then NASA will plan a future mission to fly to Mars, pick up that cache of 30 samples and bring those samples back to Earth. That retrieval mission is not funded at this point. Okay, the instruments that are on this rover include the basic navigation and computer systems that a rover needs. So it has stereo imaging, it has zoom and panorama modes, it has instruments to detect the mineralogy of the soil and rock around it, and a computer to allow the rover to navigate by itself through the rough Martian terrain. It has a series of environmental monitors, which are intended primarily to gather data for any future manned missions to Mars. So it's going to accurately keep track of all the temperature at all the different situations, moments in time, locations, and so forth. Keep track of the pressure, the humidity, the wind, and the dust. Dust is a key issue on the surface of Mars, so they want to understand in more detail the distribution of dust in terms of the size and the shape of the dust particles. It also has a device called MOXIE, which is capable of extracting carbon from carbon dioxide oxygen molecules. And that would be very important for future manned missions. Humans need oxygen to breathe. There isn't any significant amount of oxygen in the atmosphere, but if you can extract the oxygen from carbon dioxide, then you don't have to bring oxygen with you from the Earth. Oxygen is also half of the fuel that's required to bring a rocket back from the surface of Mars to Earth, the other half being hydrogen. So if we can manufacture oxygen on the surface of Mars in a convenient way, using power from solar panels, then that would make future manned missions much more practical. So this is the first test of this technology to see how much oxygen we can make under what conditions. The rover also has high-resolution chemical analysis provided by an X-ray fluorescence spectrometer. It has ground-penetrating radar. It has an ultraviolet laser, which is a Raman spectrometer, which provides high-resolution mineralogy and analysis of organic chemistry. And it has a laser imaging system to identify potentially organic compounds from a distance. So it can shoot its laser out, look at the rock formations in front of it, and find the most promising, and then go take those.
A quick question, Robert.
Yeah.
Okay. All these various technologies are coming from various labs like Johns Hopkins and places like that. This is not all JPL in-house technology, is it?
You're right. For a variety of reasons, it's important to NASA to involve lots of different groups in all of these missions. So JPL is the lead group, the integrator of all of these things, and ultimately responsible for the success of the mission. But the French have contributed, the Canadians have contributed, various American institutions have contributed. I'm sure there's a contribution from the Europeans in this. And a lot of that is because these people all have great technologies that we want to take advantage of. And also we want to make this a community effort. And they provide a certain amount of funding.
Right. So if you're interested in a particular, for instance, ground penetrating radar, you can go and find the technology there in the lab that produced that and get smart on that particular instrument.
Yeah.
Okay.
This is the official name, RIMFAX. So if you Google that, then you'll find out who made it and what the key parameters of the technology are.
Super. Thank you.
none of this is my personal expertise, so I try to give you references. One of the innovations that the Mars 2020 mission will have is that it includes a helicopter. And this helicopter is like a scout. So it can be sent out and examine the terrain at the far distance, much further than the rover can detect with its own fixed instruments, and then communicate back to the rover, and hopefully this will be an advantage. It will allow the rover to go to the right place the first time. Now, this has never been tried on Mars before. Mars has, as we noted, a very thin atmosphere. So it's not 100% clear that this is actually going to work. It's called the Ingenuity helicopter. As I said, the Martian atmosphere is about 130 times less dense than Earth's atmosphere. It's 6 millibars. So the helicopter has 2 rotors, which are 4 feet long, which is quite long considering the dimensions of everything that has to go into the craft. And these rotors spin at an extremely high rate of 2,400 RPM because they need to spin that fast in order to generate sufficient lift in the very thin Martian atmosphere. The rover is entirely powered by solar panels at the top, and the whole thing weighs 4 pounds, which is really incredible that you can pack all this technology into 4 pounds. It has a communication system to link it to the Perseverance rover. It has its own computer system. It has 2 cameras and its own navigation system. Now, let's talk about the soil samples and what we might anticipate in the very best case. Now, this is not from Mars. This is from Earth. This is called a stromatolite, and what it is it's a sedimentary deposit found in the rocks of Western Australia. It's from a particular part of Western Australia where those rocks are among the most ancient rocks on the surface of Earth. Excuse me. These rocks are in excess of 3.5 billion years old. So there hasn't been any tectonic remodeling of the surface of that part of Western Australia for billions and billions and billions of years. And so these ancient formations are just as they were all this eons ago. And these are layers upon layers of deposits. I flipped it on its side so it would fit better on the screen. So this is up and this is down. And it's fossilized, but you can see that there are organic materials that are inclusions in the rock. So if you take this Earth sample and you take an X-ray fluorescence spectrometer, then you can identify these organic compounds in green and orange in these layers. And this is something that the Perseverance rover will be able to do at some level of precision, not the same precision as we would be able to do if we had the sample in our labs on Earth, but it's sufficient to give us the idea that the samples would be worth pursuing. This is a scale bar down here that's 1 millimeter, so these things are quite small. So this is a stromatolite, and it is generally accepted to be the evidence of the oldest life on Earth. And that dates to 3.6 billion years ago, which is about 1 billion years after the formation of the Earth and less than 600 million years after the surface of the Earth was no longer molten. So this is evidence that life on Earth evolved in no more than about 600 million years from the point where the surface was molten, which prevented the existence of life, until the appearance of life. It obviously, life could be older than that. Okay, so this didn't take nearly as long as I thought, so maybe I went through too fast. So we have time for lots of questions today.
It sounds to me like this is a direct application of the artificial intelligence from my computer background.
Okay. In what particular way?
To gather information and make adjustments without other involvement. On its own, it is capable of sensing certain parameters and using those parameters results to decide to do other things.
Yes, yeah, absolutely. And it's more efficient that way.
I understand.
Yeah,
Yes.
because it just takes a long time to get sensor information from the surface of the planet back to Earth, and to have people think about it and then decide what to do and tell the rover how to move. And that's a very tedious process. So the more the rover can do by itself, the more effective it's going to be. Yes. And, this is not easy to do.
No, that's a very complicated function.
Yeah. So JPL has been, developing this over, certainly more than a decade, right? I mean, the first rovers on Mars were more like 20 years ago, weren't they?
Yeah.
Robert, I wanted to ask you, have other countries who have apparently been doing similar kinds of things up until the rover. Is there any evidence of possible interference with their they have rovers, or like the Emirates and the Chinese, and are where we're landing, is that going to have anything to do with where they have landed?
Your audio broke up a little bit, so let me tell you, Gil, what I heard, and then you tell me if that's what you said.
Okay.
You asked whether there were other rovers from other countries on the surface of Mars.
Essentially, yes.
And I think the answer is no. Also, there has never been a rover sent by anyone to Jezero Crater before. So this is virgin territory, and we won't bump into anything. I think it's going to be a long time before the Martian surface gets a traffic jam.
Good one, Robert.
Robert, there's a term called regolith, which has to do with dust, like has been found on the lunar surface, and is expected to be found in some form, but not as dense on Mars. Is there anything that you know about regolith?
I don't have any specific information about regolith, but there is certainly a lot of dust on Mars. I mean, there are particles on the surface, and there's particles in the atmosphere. And Mars is notorious for its dust storms. So these dust storms can last as long as a year, and they can be very violent and hazardous to both the rovers, and if we had manned missions up there, they would be potentially hazardous to the astronauts. I mean, they would have to be in shelters during these dust storms. So part of the environmental monitoring capabilities of the Perseverance rover are to gain more information about the prevalence of Martian dust. Oops, someone is just joining now. That's
How does, Robert, how does the dust storm come about since the atmosphere in Mars is so thin?
yes, it
How
is.
how do they get this wind to come around?
I don't, I'm not a geologist. I don't understand these things as well as I should, perhaps. But the winds on Mars can be intense. And the dust is very abrasive. Part of the problem that JPL has encountered on past missions, including the Curiosity mission, is that the Martian dust eats up the tires and gets into the mechanisms of the rover. So they've had failures in the past on previous rovers, and they've had a degradation in performance on the Curiosity rover because of all this dust.
Robert,
Yeah.
I use my location as an example of the variety of weather conditions that could apply there as they do here. So I don't know how to recognize the difference in conditions that might moderate the high winds and other challenges that are physical challenges that the probe might encounter. And the way to find them escapes me also. Over.
Okay.
So, Robert, follow-on question, maybe two also. I'm sorry, all I can see is K5KT Joe about artificial intelligence. When you were describing the descent and landing, it is making autonomous decisions in terms of the optimal landing site. But once the rover is deployed and on the ground, is the rover itself making autonomous decisions about its direction / route of travel?
I think it makes this autonomous decisions to a limited extent. I think that humans will still have input direction into, for instance, which part of the terrain we're going to go to, but those decisions will be made subsequent to the rover gathering the sensing information that indicates what would be more promising. The rover probably also has some autonomy in terms of its actual motion to get to the destination.
Okay, so there is a little bit of artificial intelligence embedded in the rover software.
I believe so, yes, more than in the past.
Okay, thank you.
Robert, I was rewatching the Martian movie, which they obviously put on now for those of us who are interested in watching the actual February 18th landing, and it was very interesting to know that the terrain from the Martian that they used was filmed in Jordan in a Bedouin, outside of a Bedouin camp called, I think it's called Kuva Rao. And if you look on Google, you can actually see pictures of it and what the terrain looks like from the movie, which simulates what the actual Martian surface looks like. and they also had some discussion about making water as well as making plants in the form of potatoes while he was on the moon, and how much science in effect contributed to the making of the movie, that this was not altogether, a bizarre science fiction movie. This is, a lot of it was based in fact.
I see.
Or our understanding of the facts.
Right, our understanding of the facts before we land there. Right.
Well, there's a strong group of people who are promoting the colonization of Mars. And if humans actually do establish a long-term colony on Mars, we're going to have to that colony is going to eventually have to be self-sustaining.
Right.
So we have to find ways to grow food on Mars. We have to find ways to get oxygen. We have to find ways of getting water. It's a very inhospitable place.
So what else is this Mars program going to do in Mars after all is done on what they initially wanted to do? I suppose it's going to stay there, but it's got to do something.
Yeah, these rovers, they will run as long as they're capable of running, and continuing their exploration as long as they can, and then at some point they just are turned off. So it costs NASA money to continue to have humans interacting with these devices. So if the devices aren't sufficiently productive, they just are, we stop taking care of them, and the devices become part of the Martian landscape.
What is Elon Musk planning to do in Mars that's related to this program?
I guess he's looking for a new market for Teslas. Maybe he can get a version of his Tesla that will run across the Martian terrain.
It's a little bit early, but good try.
Well, it's exploration, and the first objective of exploration is to learn what's there, and see how we can use it to our advantage. There are people who think that, one of the topics we can talk about in the future is, what is humanity going to do when Earth is no longer a habitable planet? And, that we have maybe 600 to 800 million years of continued habitation on Earth. And after that, the surface is going to no longer be habitable, because the intensity of sunlight is going to be high enough to have lead melt on the surface. So I guess we'll bore down into the ground for a while, but eventually that's not going to work either. So at some point in the distant future, a billion years from now, whenever it is, humanity has to have another home, or humanity will end. Now, not everybody wants to worry about that. It is a billion years off, but there are people who do. Let me also add, I guess, that if we did find a way of establishing a colony somewhere other than the Earth, that would not mean that 7 billion people would be transferred to that colony. The number of people that we would be able to launch into space to populate a colony is going to be dozens at most, not billions. So the species may survive, but the vast bulk of the population is not going anywhere.
What
Anyway.
about
Mhm.
exploring whether there's been life in the moon or not? Seems like a logical landing place and place to settle.
Yeah, it's a lot easier to get to. The moon is a lot less habitable even than Mars.
However,
However,
the
well,
moon
if we're
orbits the Earth and therefore would enter the danger zone that envelops or envelops the Earth also.
yes,
So it can be marginally possible, but
yes,
only for part of the time.
it would not extend our existence very long.
Right.
Mars is significantly further from the sun, so it would be less affected by the sun's increased radiation, and in fact, that would make the planet warmer, which might make it even more habitable than it is now.
Plus, by then, we may have means of discovering habitable alternatives out there and the means to reach them that we don't have an understanding about today.
Yes. So there was an interesting article in the scientific literature this week about a scheme to get people to a planet around a nearby star. And to do that in a much more sensible way than previously proposed. And it's an interesting idea. It could be the topic of a future seminar if you guys are interested in it. Basically, what they're saying is if you wait long enough, some star is going to come close to us so that we don't have to go as far to get there. And they do a calculation of the probability of some star coming close enough that our rockets could reach it. Now, we wouldn't go to the star, of course, we would go to a planet orbiting the star, but
I think that's a great class for you to teach.
okay.
What about the Andromeda galaxy coming close? Would that provide us with options also?
Well, the Andromeda galaxy is going to come close. I think it's about 4 billion years from now. It's going to collide with the Milky Way. My first impression of that is it's going to be very hazardous to every form of life that may exist.
And too little, too late.
And by then the sun will make the Earth no longer habitable long before then. So,
Okay.
yeah. Okay, so Mars 2020 is going to land on Thursday at about 12:30 Pacific time. And I'm sure that it's going to be broadcast. So I don't know what the channels that you can look at are, but if you search for Mars 2020, I'm sure that NASA will provide you with the appropriate information to monitor the landing. And hopefully from today's discussion, you'll have some appreciation for why we're doing it and what we might get out of it. I could say a few things about our next seminar series, if you wish. This is the last of the 6 seminars of our second series. And the next seminar series begins on March 9th, which is the second Tuesday of March. And we're going to, the first topic will be the birth of relativity and how the birth of relativity, the theory of relativity was enabled by a better understanding of the properties of light. There are a couple of topics that we will be including in the third seminar series. We will be talking about the Large Hadronic Collider and what they've discovered and how they search for new particles and what the prospects are for the Large Hadronic Collider. We're going to have a topic on science and faith. And then we have some openings. One topic I want to talk about is fast radio bursts, FRBs. This is one of the hot topics of astronomy these days and one of the fastest developing topics because we have only recently discovered them in the past 15 years or so. And we have, so we discover new things faster about the fast radio bursts than many other things. There have been 2 interesting articles in the scientific literature in the last week, which make interesting proposals as to what might be generating these fast radio bursts. Other topics we can talk about include black holes. And someone has requested, one of you has requested a discussion of nuclear fusion. So that would be 2 seminars. So the first seminar I envision is to understand what is the process of nuclear fusion. And we're going to begin with the quantum mechanics of barrier penetration. That if we understand what barrier penetration is all about, then we'll understand what nuclear fusion is, and we'll also understand what radioactive decay is. So we'll have one seminar about those 3 topics. And then the next seminar will be about how we may in the future be able to use nuclear fusion as our primary source of power. So nuclear fusion is not something that needs to be invented. It exists in nature. It's the way that all of the stars in the universe are powered. What needs to be invented is the engineering to make it feasible in a controlled way in a machine on Earth.
And safer.
It's intrinsically safer than fission. It's clean. The fuel is unlimited in its abundance. It does not generate toxic waste. It does not generate greenhouse gases. And it is in principle dirt cheap because you're just burning hydrogen and the ocean is full of it. So it could be, it's also 40 million times more efficient than burning coal.
Wow.
So that means that it doesn't generate pollution because you're using so much less fuel, and it doesn't, in principle, the cost of the fuel is going to be very minimal. This is the way nature makes energy. Nature doesn't pollute. Nature is efficient. Nature has had a long time to work these things out. So nuclear fusion is the ultimate source of energy in the cosmos, and it's something that we may possibly be able to engineer into a practical system.
Robert, doesn't fusion take huge heat that we haven't been able to generate the right amount of heat here on Earth yet?
Yeah, it takes, nuclear fusion occurs in stars at temperatures of 20 million degrees and above. And we can't make an oven that gets the 20 million degrees because every element on the periodic table melts before that. So we have to be smarter. And we have had some relatively clever ideas, but we've had no genius breakthrough yet.
Oh.
So we're still working on it. We have had some success in creating nuclear fusion in the laboratories. Obviously, we know how to make nuclear fusion in bombs because that's what the hydrogen bomb is, but that's not controlled. And that's not safe, as Joe said. But we have done nuclear fusion in laboratories in at least 2 occasions. We just haven't made it commercially sensible,
Okay.
which it would have to be.
Thank you,
And-
Robert.
And then we have a whole raft of other topics about cosmology. We can talk about neutron stars. There have been some interesting new developments about neutron stars. We can talk about the distance ladder of cosmology. How do we know the distance to a star? How do we know the distance to a galaxy? It would be nice if we had an instrument we could point at the galaxy and it would, a number would come up on a screen and says, "Is this far away?" We don't have anything like that. And so the way that astronomers figure out the distance to a star is actually very intriguing. And it's the greatest problem in the history of astronomy and still continues to be the greatest challenge in astronomy. So that's a great topic. We can talk more about the next generation telescopes. There are even proposals to put telescopes on the moon, where we could make even giant ones. There have been proposals about proposed topics about entropy and symmetry, and the list goes on and on. So in about a week or so, I will send an email out to the people who are registered for the 3rd session and gather your votes for the topics that are of most interest.
So, Robert, can I add maybe a subset of one of those things that you thought you might present? A couple of years ago, I had the pleasure of going with Jill to Switzerland to the Large Hadron Collider, I guess would be the right phrase. And one of the things that they were talking about was the data processing. It takes the capturing of the results of the collisions and then the data processing that takes place, and somehow they sort from all the data the relevant or the most interesting phenomena for human beings to then look at. And I was mystified how you capture all this data, how do they zero in on what of this huge amounts of data represents interesting results of the collision? Is that something you could address?
Yes, I think they keep less than 1,000th of the data. So they have an automated sorting algorithm to try to find the more interesting events. And what they're looking for is the telltale signs of high energy processes. Their position is that other accelerators, which have been running at lower energy levels, have combed through the low energy stuff in great detail, and the Large Hadron Collider doesn't need to do that again. So what the Large Hadron Collider can do that the others haven't been able to do is extend the energy frontier. So they are looking for events in which there are signs of great energy release. In particular, if you look at the transfer, there's a lot of longitudinal energy in the beams, and they can bounce off each other, and that isn't terribly interesting. But when something happens that converts that longitudinal energy into transverse energy, then you have a possibly a much more interesting situation. So one of the key things that they use to select is the degree of transverse momentum that's deposited by the event. But in any selection criteria that's formulated by humans, you run the risk of missing something, right?
Right.
You're rejecting 99.9% of the data. And you may well be right that there's nothing there, or you might not be completely right.
So they only literally store, and then somebody analyzes a very, very small fraction of the data that's captured.
Yeah, there's more than just the two stages, I think. They immediately throw out all but some. I have the numbers, and when we talk about the Large Hadronic Collider, I'll give you the real number. But it's something like they throw out 99+% of all the data almost instantaneously, according to a computer algorithm. Then
Okay.
they store the rest, and the rest is a volume of data that would sink a battleship.
Wow.
And that data is then sifted again by computers. And before any human looks at a picture, it's probably gone through multiple stages of computer filtering. And even in the final images, if you look at some of those events, they can be hundreds of particles coming out of a collision at the Large Hadronic Collider. There's so much energy available in the center of mass to produce. And if a human looks at a picture like that with hundreds of particles coming out, your mind just goes into overload. I mean, I couldn't look at a picture like that. I mean, I've seen thousands and thousands of high energy physics collisions recorded in various modalities. And, you know, I could pick things out in one of those images. But when you have hundreds of particles, you know, you just can't, the mind can't cope with the complexity of that. So in the end, it's all computers.
Okay. And then that data is available to, that subset of the data is available to scientists all around the world through this, the
Yes.
impressive network.
Yes, that's publicly, the final results are publicly available.
Okay, thank you.
Yeah. Okay. Anybody want to ask any other questions or make a comment or?
Well, I learned a lot again today, I can tell you.
Oh, thank you, Diane. So I hope you have time to enjoy the landing and see the action. It's one of the great things that American science does,
Brilliant.
with the aid of the rest of the world too. Okay, I want to thank all of you for attending today, and I hope to see all of you on March 9th. We'll talk about Einstein's theory of relativity and how it came to light.
Thank you
Goodbye.
very much, Robert.
Yes, Charlie.
Enjoyed it.
Thanks.
Thank you.
Please thank Joan for doing a great job
Yes.
making everything so perfect.
Yes.
Robert, you're the best.
I always thank Joan.
Good.
Thank you, Jill.
You're welcome, Joan. You're great.
Thank you, John. Nice to
I
meet
have-
you.
I have to tell you guys that let's see, today's the 16th.
Yep.
Next Tuesday is our 52nd anniversary.
Oh, congratulations. Wow.
Wow. Big achievement.
May you have many more to come.
Yeah.
Thank you.
Great job.
Just think of how much she's endured.
Or inspired you.
Yeah.
Okay, bye-bye.